In the name of Almighty, good morning, one and all gathered here. I am very glad to welcome the gathering for the
Hello. Hello.
I call upon Professor Maria Pillai to deliver guest intro. Please, sir.
Okay, sir. Most respected principal, sir. Respected vice principal, sir. Beloved HOD, dear professor and participant, today resource person Dr. P. KARTHIKEYAN. Good morning to one and all gathering here. I am very glad to introduce our today resource person Dr. P. KARTHIKEYAN. Dr. P. KARTHIKEYAN, MSc, MPhil, PhD, PhD, Associate Professor, Annamalai University. Professional experience. Our resource person has 73 years teaching experience and 25 years of research experience. Area of specialization. Our research person current specialization is nanomaterials and vibrational spectroscopy, computational chemistry, bio-inspired material. Research supervision. Under his guidance, previously student completed ongoing PhD for MPhil 10 research publication. Our research person published more than and more than 20 national level papers in the various reputed journals. Since Google Scholar, the Scopus value is 43, H value is 15, I10 index value 23. Our resource person sponsored project, completed two projects, one project ongoing. The total amount of budget is 16.23 lakhs. Book published. Our research person chapter published in elsewhere. Conference symposium. Our research person attended and conducted various national and international level conference. Honors and awards. Our research person have won Raman Fellowship Award USA. Foreign visit. Our research students visited various areas in and around the country. Hungary, IR sponsor, USA, UGC sponsor. Other contributions.
Other
Our resource person
our
are
resource person
IQAC
are
nodal officer,
IQAC nodal officer,
Y mentor,
mentor,
counseling committee member in
counseling
5
committee
years,
member in 5 years,
and invited speaker for
and
various
invited
colleges.
speaker for various colleges.
Still in ICT enabled teaching
In
in
ICT
MOOCs,
enabled teaching,
installed smart classroom in the
installed
activities.
smart classroom in the activities.
Our resource person is live
Our
member of
resource person is live
CRSI
member of
and
CRSI
LHSI.
and LSSI.
This is the brief introduction
This is the
about
brief
today's resource
introduction about
person, Dr.
today's resource
B.
person,
Karthikeyan.
Dr. B. Karthikeyan.
Thank you, sir.
Thank you, sir.
Thank you so much, sir. Thank you for your guest intro. Now I hand over the time to a resource person.
Yeah. Good morning, all. Good
Dr.
morning, all. I am very happy to share my research work, and at the same time, I can tell some introduction or sensitization to the students of
Of
college, your college, and I'm very happy and thankful to the organizers, Dr. Jayseelan, Dr. Kamalakan, Dr. Senthil Raja, and Dr. Veerapalli, and all faculty and students who invited me to give a talk on that exploring chemistry from computation methods. When I teach PG research students at the Department of Chemistry, I learned that some fundamental topics are very, very important, like group theory, quantum chemistry. These are all very useful to know the structure of the molecule which we can't see with our math. What is the difference between chemistry and other subjects? Chemists have to be not they have to think as if we are seeing molecules with our eyes. So we should know the atom properties, how atoms are joined to with bonds, and how they make structures, and how the structures are different. Maybe a 6 member ring, it may be a double helix structure, complex DNA, a protein structure. How structure is going to be very important. So to know the structure of an unknown molecule, which we can see with our naked eyes, we have to use different techniques. We have to use spectroscopy, we have to use X-ray crystallography, we have to use computational methods. And computational methods are little cheaper when compared to whatever techniques I told, spectroscopy or XRD, because computational softwares are freely available, and sometimes we may get license and we can work on that. And what is the basic of these computational methods? We have to go back to our classroom and whatever we have learned in our MSc chemistry or BSc chemistry, what is called group theory. Group theory tells structure of your molecule, whether what is the axis, C2 axis is there, or C3 axis, or D6H, whatever symmetry operations we can do to get back the molecular structure again. This all tells you different aspects of molecular structure. So, from the basics of group theory and quantum chemistry, we can I will tell some important how quantum chemistry evolved in later slides. So, with this introduction, I'm going to the next slide. So, I start with as my passion is in materials, whatever we learn in our periodic properties of our first BSc class, start with microbiology and protein production and goes to internet. Now, this periodic table figure tells you how different materials are associated with each atom molecule. Hydrogen is useful in rockets. Lithium, every day we are using it in our cell phone, our element, and you can see the application. You can wonder, we may wonder how we are all using different metals in everyday or different elements in everyday life. Of course, we can't see all this in our naked eyes. These atoms make molecules, and molecules make big molecules or dendrimers or self-assembly. It goes to bulk matter that we are using. That all we are going to discuss. How computational method is useful is how it is going to address the properties of bulk by addressing small molecules. So students, because this talk is aiming to touch the students, I want to tell the students, you just watch these slides and you can analyze how the small things, whatever we learn in our classroom, it is going to going to be applicable to the society. So we may think in our classroom, group theory is boring, quantum chemistry is boring. Why we study? Why we are all studying this? We are doing laboratory work, but here group theory and there is nothing is there. Only structures are there, and it may be dry. But I'm going to tell how now we are all in pandemic situation like COVID-19. So what we are thinking, we have to get some medicine to tackle COVID-19. So for that, what is the basic criteria? We should know the structure of the virus. If you know the structure, but unfortunately the virus is structure changing, so people are struggling to get the appropriate drug for that. But anyway, we hope sometimes the chemist, biochemist, molecular biologist, virologists all will find a drug or vaccine. So docking is very important nowadays. Instead of doing all kind of trials in lab or human, we can do a docking in computer and we can find a potential targets for this type of diseases. So the simple thing, whatever the fundamental we learn in our classroom, will make you a good scientist. So student friends, you can think about these things in your mind, learn the fundamentals properly, attempt all the questions like CSAR, NET. You can take the questions of that and try to attend that and get knowledge. And after your MSc, if you have time, you can join PhD and you can do or you can work on that and you can find the applications of chemistry. So the next slide will tell you, as you all know, what you are seeing in the slide. So this is a comparison slide. So how nanomaterial, because why I introduced this slide, after the invention of microscopy, whatever the invisible things to the eyes are becoming visible. Even now, atoms or molecule can be visualized through electron microscopies. So I want to tell the students, no longer chemists are finding the solution only with spectroscopy or computational method. We can add microscopy, and microscopy give the direct evidence. So when atom and bulk matter, I told atom and bulk matter, in between there is a neglected dimension that is called nanomaterial. And after the invention of microscope, these nanomaterials are now explored by the researchers, and they are having special properties when compared to atom or bulk matter. They are having special property. The bulk gold, whatever you can see, the bulk gold is having shiny yellow color, but when you go to the nanomaterial scale, it color changes to red or pink color. So this is a change when the atom or bulk matter goes to the between stage nanomaterial. So the optical property is completely changed. So now I can tell the bulk goal what we teach in our classroom, it is inert. That's why I am telling it is a noble matter. But when you make nanomaterial, it acts as a good catalyst. So the entire property. Now, no longer gold is a catalyst or not. Yes, the bulk gold is inert, but nano gold is catalyst. Many organic reactions are now catalyzed using nano gold, nano silver, nano platinum, nano copper. So all becoming now the properties are completely changed. So we, the chemist, BSc or MSc or research students, we should know these 2 points. One is it is all new, the change environment in chemistry. No longer atom or molecule are not visible. We can see atom and molecule by sophisticated microscope, and we can alter the properties when you tune to the nano phase. And how we can see atoms and molecules? How we can see atoms and molecules? Kekule got benzene structure only in his dream. I used to teach to my students. I ask, why you are all sleeping? Then they tell, sir, we want to become like Kekule. We may get some structure in the mind, but only Kekule got only one compound benzene structure. Of course, benzene is a ring structure, but only we are having thousands of lakhs of molecules. The structure has been solved only through spectroscopy. You can know IR, Roman, NMR, ESR. This all useful to elucidate structure of molecules. We are studying this in MSc classes, how different UV visible spectroscopy are useful to arrive the structure of a organic molecule or inorganic complex. And XRD, X-ray crystallographic techniques we use for getting structural information in solid state. So many proteins are solved. The structure complex structures has been solved by X-ray crystallography. You know that Watson and Crick, they solved DNA structure. They showed it is a double helical structure only through XRD. So now we know well on DNA molecule only through XRD, and we are all finding DNA target medicines. So, and recently Venkatraman Ramakrishnan got a Nobel Prize for solving the structure of ribosome. Ribosome is having more than 20,000 atoms. He solved by only through XRD technique and microscopy. So the new technique we may add to see atoms and molecule is a direct evidence. Whatever spectroscopy, XRD will give indirect evidence, and we have to work or we have to solve from chemical shaped or bond angle, dihedral angle calculations. We have to arrive the structure, but microscopy will give direct eye to eye how the molecule looks like. So I am showing some figures of molecule in this slide. You can see the molecule. This is the molecule when we go to the microscope, and it shows almost the direct visualization. What microscopes are used? You can see scanning tunneling microscope, atomic force microscope, and there is another one thing. It's very simple. We can use our computer. A computer loaded with softwares like sophisticated Gaussian or Schrodinger or available quantum chemical calculations will tell you how the structure looks like, and what is the structure and what is the energy of that structure, what is the thermodynamical values, what is which orbital is highest occupied, which orbital is least occupied, and what is the electrostatic potential, and how solvent affect the properties, solvation effect, everything the uh, DFT calculations or quantum chemical calculation will tell you. So students, you can use the freely available software in the net, and you can work out and you can take a molecule and do a calculation and get some properties and compare the properties with your textbook values. Suppose you take simple water molecule, because I'm a physical chemist. We always take water as a molecule, a simple molecule, triatomic, and we used to optimize water. From that structure, what are the inference we can get? A simple water will tell you what is the bond angle between two OH bonds, and what is the hybridization, what is the dipole moment, what is the polarization, whether it is IR active or Raman active, and what is the why it is called universal solvent. This all can be, what is the stretching frequency in infrared, what is the stretching frequency of water in Raman, why IR gives strong band for OH in water. All can be, you can theoretically you can compare with the experimental result. From that you can know the properties of a simple molecule and how it is going to be affect a large scale. Because if you analyze a atom or a single molecule, it may compare with the bulk molecule. So now I will come to the calculation part. So I advise students, you can go to the software or you can go to the internet, get a quantum chemical calculation. Of course, you can see that slide. Anyone can do calculations nowadays. You can see all colleges, universities, they're all started computational work. Anyone can also operate a scalpel, scissor. That does not mean all our medical problems are solved. So there is a problem. Uh, Anybody can use calculation, but judicial use of calculation is needed. Whenever you need some important properties, you can use DFT calculations instead of thinking about only this will do the entire research. We can use this adjunct to our experimental research. So I'm interested in experimental research. At the same time, I'm more interested to do theoretical when it tells or when it supports of my experimental results. So many experimental chemists use various kinds of spectroscopy in their research, even though they are not spectroscopists. In a similar manner, more and more scientists are applying computational techniques as another weapon in their arsenal. So now computational chemistry is one of the most rapidly advancing and exciting field in the natural sciences, not only chemical sciences, physical sciences. Now even biologists are started using quantum chemical calculation. So when the Dr. Kamalkanan asked me, I decided I have to tell something to the students instead of group theory or quantum chemistry, how they are going to be useful for the real research life. So I have taken this topic, and I hope all will get some idea after this talk. They may start using computational chemistry in their field or in their career. And what is the use of calculation of molecular structures and properties? Molecular structure and molecular properties by quantum chemical method, uh, we can divide into two major subdivision. One is computational chemistry, another one is molecular modeling. Why computing molecules? Because instead of doing so many molecules in the laboratory, we can simply take a parent molecule and we can compute some properties, and we can substitute some substituent, and we can calculate, and instead of doing again back to the lab, all can be used. So electronic structure theory can be used as a very useful tool, providing new insight into physicochemical properties. Nowadays, we are all talking about green chemistry. We have to go for greener approach. You know that instead of going qualitative analysis in the lab, now we are all thinking about small, mini, micro level testing. So recently I have attended a talk on micro level testing. They use a small wet white cloth for doing reactions instead of test tube in our normal laboratories. So people are thinking about miniature and sometimes virtual laboratories. Now in the pandemic situations, people are thinking about virtual laboratories. Instead of going to the lab, the whatever we are doing in the lab will come to your screen, and we can do it and we can get the information. By doing that, we are all protecting ourselves from the pandemic. At the same time, we can reduce the chemicals. At the same time, we are getting knowledge and in safer way. So computing is one of the tool, so we can safe in our home, and we can do whatever research or whatever we are attending conferences virtually, and we are doing research also by doing chemical calculation will give you some new ideas. So we may find some new ideas for the future. So now we are all moving to the new platform in the pandemic situation. So we can think about the new avenues and major goals in a computational chemistry. Whenever we start a computational calculations, first of all, to create efficient mathematical approximation and computer programs, we need efficient mathematical approximation. I think MSc students, you may know that 44 approximation, which tells nucleus is much heavier when compared to electron. So we can intact nucleus and we can calculate only electronic properties by considering electronic wave function. So this is for 44 approximation, which gives you use calculations, or you can go for calculation for very big molecules. So approximation and computer programs like Gaussian is really helpful. Uh, I have used Gaussian 03 in my research, and later it is upgraded to Gaussian 9. Now Gaussian 16 is available. So using these kind of softwares will definitely help you. To calculate the properties of molecule, what are the properties we can calculate? Total energy, dipole, quadrupole moment, vibrational frequencies, reactivity, different spectroscopic quantities, and cross section for collision of molecule with different atomic or subatomic projectile. Whatever the goals is different for different people. With biologists, his goal is maybe find out a good target for a good protein, and because now you can think about a good target molecule which interact with H1N1 influenza virus. So this is a goal for a biologist or a medicinal field people. Our chemistry people, we are thinking about new drug molecules, and material science people will think about a good material with good electronic properties like semiconductors, and like that the goals will be different. And how computational chemistry is useful. Computational chemistry is used in a number of different ways. One particularly important way is to model a molecular system prior to synthesis. So, suppose you want to do a synthesis. You are going to synthesize some new drug molecule. You can do a computational chemistry analysis before going to the uh, uh, bench. So, by doing computational calculation, we may tell what is the thermodynamic property, whether it is stable or unstable, whatever thing we can predict. The second use of computational chemistry is an understanding a problem more completely. So we can analyze, not only give the structure, at the same time we can tell the potential energy scan we can do, or we can do different solvation models. We can give the mechanism. There are some properties of a molecule that can be obtained computationally more easily than by experimental. Suppose electrostatic potential of a molecule can be analyzed very easily by doing calculation instead of going for experimental. And what are the computational, what are the methods available? So I'm going to tell what is semi-empirical method. I think you may see this semi-empirical methods in different places. People may tell I'm using semi-empirical, somebody tell I'm doing a Vincio calculation, somebody may tell I'm doing DFT calculation. What is semi-empirical method? Semi-empirical calculation was set up with the same general structure as a 44 calculation, in that they have a Hamiltonian and a wave function. I hope Hamiltonian is operator which gives energy of a molecule. So if you want to know the energy of a molecule, we have to do a optimization, and optimization will give you a lowest energy structure, and within this framework certain pieces of information are approximated or completely omitted. So in approximations we may omit some of the things and try to get some desired results. Usually the core electrons are not included in the calculation, only a minimal basis that is used. You can see 631 G star, 321 G star. These are all depends on which electrons are we are going to take, or we are considered for the calculations. So in AM1 semi-empirical, some of the example is AM1. AM1 is the as Austin model 1. This is a semi-empirical method. Depending on the nature of the system and information desired, either AM1 or PM3 will often give the most accurate results obtainable for organic molecules. So sometimes instead of going for DFT, AM1 will give you good results for bigger molecules. So you should know that. And what is ab initio? Ab initio means in Latin from the beginning. So we go to the quantum chemistry uh, basics. This name is given to the computation that are derived directly from theoretical principles with no inclusion of experimental data. So we are using only the theoretical data, and we derive some theoretical data. The most common type of ab initio calculation is multi-pop calculation, in which the primary approximation is the central field approximation. This means that the Coulombic electron-electron repulsion is taken into account by integrating the repulsion term. So you know that in a nucleus, there will be uh, a neutron, and there will be a proton, and outside there will be electron. The atom gets energy by the repulsion. The molecule will get energy by the electronic repulsion and attractions. So we have to take into account this all to calculate when we calculate the total energy of the molecule. So computational method is trying according to its level. It tries to get the energy of your molecule. So the lowest energy structure is the optimized energy. We are going to tell this. And this structure, what is the lowest energy structure? Where atoms are sitting and enjoying the place without any hindrance. So this is the least energy structure that can be obtained through these calculations. One of the advantage of this method is that it breaks the many electron Schrodinger equation into many simpler one electron equation. We know that still Schrodinger equation solve only for single electron molecule, single electron system, for one electron system. So what we can do, if we have multi-electronic system, we can divide the into many simple one electron equation and try to do that. That's why you can see some calculation will run for take 2 or 3 days. This is because of it solving the big molecule by integrating, by dividing into one electron equation. Finally it integrates. Each one electron equation is solved to yield a single electron wave function called an orbital and an energy called an orbital energy. So it calculates orbital energy, and finally it calculates total energy. The second approximation in HF calculation is due to the fact that the wave function must be described by some mathematical function which is known exactly for only a few one electron system. Set of basis function used is often by an abbreviation, often specified by an abbreviation such as STO3G or 631G star. So people use DFT calculation without knowing what is that. Some examination or viva voce, if they ask the question, what is 631G or what is YSTO3G you used, and you have to tell the answer. So I took this slide and I want to give. And the primary aim of computational method is determination of the equilibrium geometry. Generally, the geometry associated with the lowest single point energy. So what we can the first primary goal is geometry optimization. So it can be also used to find transition state geometry. So it is little more tough. Sometimes when you do the calculation, it may go to the lowest energy state generally. Instead of that, sometimes it may goes to transition state. So transition state that can be verified only through frequency calculations that I can tell later. But now you realize that all molecules, the lowest energy structure is optimized structure. And SCF theory finds a stationary point, a place where the energy gradient is zero, may correspond to either a minimum or saddle point. What is saddle point? Here the graph will tell you what is the saddle point. So this is our potential energy, whatever we learn in two-dimensional. When you see three-dimensional potential energy surface, when two potential energy surface cross each other, there will be a saddle point, there will be a global maximum, and there will be a global minimum. So theoretical calculation will look for global minimum. So the optimization means we are looking for global minimum structure. And frequency calculation, so we whenever we do a calculation, theoretical optimization, we may do frequency calculation also. And what is frequency? I think you all know that frequency means, here I am meaning, the meaning is infrared and Raman frequencies. It predicts the intensity of the vibration associated with the molecule. So this is useful for predicting the absorption spectra of compound. So we can do a absorption spectra, simulate. We can simulate absorption spectra. We can simulate infrared Raman spectra. We can NMR spectra can also be predicted. So instead of doing all experimental things, we can use theoretical calculations to predict infrared, Raman, NMR, and many spectra. So going for an instrument and taking spectra takes much time. At the same time, and we can do a simulation. So it can be compared with our experimental frequencies. And those research scholars, the computational methods are which journals generally publishes this result. Journal of Molecular Structure, you can see people are publishing all structural aspects of molecule, whether it is inorganic or organic, in Journal of Molecular Structure, Geochem, Molecular Spectroscopy, Chemical Physics, Letters, International Journal of Quantum Chemistry, and chemical reviews, theoretical chemical reviews. You know that it is a highly cited review journal, and the impact factor is more than 20. So research scholars may know that chemical reviews is good. And research findings include, what are the research findings you can include with the computational tool? Scaling calculated vibrational frequencies, calculation of NMR spectra, calculation of ESR spectra, computational studies in molecular electronics, modeling intra and intermolecular hydrogen bond. So hydrogen bond, I think you all know the importance of hydrogen bond. DNA structure is stabilized only through hydrogen bond. So hydrogen bond issues can be studied through very well with uh, theoretical calculation. And large molecules can be modeled, and many things we can do. And Abincio method used to solve the molecular Schrodinger equation associated with the molecular Hamiltonian. Again, the same thing. We can not only we can go for a molecular Hamiltonian and able to provide accurate and reliable theoretical results. Even though it is computationally expensive, means it may take much time, 3 or 4 days for a single one 60 atom molecule, but it provides accurate results when compared to semi-empirical method and computationally expensive. So Gaussian program will do or will have all the specific functionalities, whatever I discuss here. It is whether it is Horty-Poke approximation we can do, or we can use different basis sets. It's all incorporated in Gaussian program. So without knowing the wave function or single electron Schrodinger equation, directly we can give a input by giving a structure, and it can write its own theoretical equation, and it tries to solve, and after once it is successfully solved, it gives the accurate results. And DFT means, so people are now talking about instead of semi-empirical Abincio calculation, go for DFT. So in DFT, what is DFT is that the energy of a molecule can be determined from the electron density instead of wave function. So instead of writing a wave function and trying to using approximation, trying to get the energy, it takes electron density. So it accounts for all electrons. So the results are being more accurate when compared to Abincio. So people prefer for density functional theoretical method. I think you all know that D3LYP, MP2, these calculations are DFT calculations. This theory originated with a theorem by Hornberg and Kohn that stated this was possible. The original theorem applied only to ground state electronic energy of a molecule. A practical application of this theory was developed by Kohn and Cham, who formulated a method similar in structure to the Horty-Poke method. In this formulation, the electron density is expressed as a linear combinational basis function similar in mathematical form to HF orbital. Okay, so this all uses group theory. So I think I will go a simple input for Gaussian calculation. How we have to give a input. So computer will recognize. Sometimes we have to write a program, then only it will recognize. We can't speak. Nowadays, even voice synthesizers all come. We are able to make artificial intelligence we want to put on computers. So it may sometimes we can order to a robot, it can do. These are all in our future. I think in our news, we are seeing robots are assisting doctors in hospitals to lesser the spread. So Gaussian calculation, we have to give you some input. What are the inputs we have to give? The input, the first, there will be a, you can see this, there will be a hash symbol, and this is the head method, multi-poke method I am going to use, and this is the basis 631G star or D. This is I am going to use. So this will tell which electrons are we are going to take into the calculation. Or this method will take only this type of electron, and it uses Hardy-Poke approximation, and there will be a root section, water energy, and there will be a title section, and we can give, and molecule specification, there will be 0 1. What is 0 1? The 0 1 is 0 is charge, so many molecules are neutral charge, so I put 0. And when 1 is comes from spin multiplicity, 2 into 0 plus 1, 2s plus 1, so it gives 1. So singlet state, so I am going to calculate a ground singlet state of water. So this is the input of recognition of water molecule. We know that water has oxygen, hydrogen, hydrogen, and this is the specification. One oxygen is connected to another hydrogen, so you can see this is oxygen is connected to one hydrogen. The same oxygen is connected to another hydrogen, and these two are connected through a bond angle. These two hydrogen atoms are connected to one oxygen atom with a bond angle. So this bond angle and bond length is the input for Gaussian to the program will recognize this is interconnected atoms or molecules. So it tries or it starts optimizing water. And if you go to the, this is triatomic. So if you go to the fourth atom, hydrogen peroxide, it is a tetraatom molecule. When you go to the fourth, there will be another term, not only bond length and bond angle, there will be a dihedral angle will come. So dihedral angle, what is dihedral angle? So the dihedral angle is the plane of these three atoms and these three atoms. H3, O1, O2, one plane, O1, O2, H4, another plane. These two planes are parallel or it is anti-parallel. So this will tell you the hydrogen peroxide structure. So hydrogen peroxide we all learn from our BSc classes, open book structure. So dihedral angle is not zero, right? So the symmetry properties of molecule can be useful. Now group theory will come. Symmetry properties will be useful in predicting infrared spectra. If you want to know the infrared spectra, describing the types of orbital using bonding, predicting optical activity, and predicting electronic spectra. So group theory will play. So by using theoretical calculation, I have calculated a IR bands. You can see that this is theoretically calculated IR bands, and this is experimentally taken infrared spectrum. So you can compare with these two things. You can see how it is matching. Right here, there is a big OH peak, and this is also we are also getting the same peak, and this all there is a CO peak. This is also there is that, and we can compare. So what is the difference between calculations and experimental? The experimental will give you the real picture with solvent, but theoretical will give only the gas phase single molecule. So there may be small difference will be there in the result that can be compared and that can be corrected, and this is acceptable in our research. And theoretical IR spectrum of a molecule, whichever I used for my research, it is adenine or some molecule related to DNA base, the theoretical IR spectrum will match with the experimental spectrum. And I try to dock a different molecule on a different this substrate. Why I'm giving this slide? So the molecule can be docked with different targets so that we can find without going to the lab whether the molecule is having potential to attack the desired target. So cancer medicine or COVID-19 medicine or structure-based drug design, this optimization or theoretical calculation is going to be very, very useful. And after getting the Gaussian output, so input is given. So according to the, it is calculating, and finally we get some results. And what how to interpret? Computation data are not a replacement for physical experiment. Of course, I'm telling we can use without experimental also we can do, but all should be verified with physical experiments. I will tell why I'm repeating this. The last slide will tell you why computational data has to be verified in by sometimes with physical experiment. So interpreting is what are the interpretation? Checking a geometry optimization with a frequency calculation. If imaginary frequencies, the negative frequencies are there, the structure of knot is fully optimized, and some of the numbers may not be accurate. So we have to go back to the calculation. We have to correct the errors, and we have to do the calculations. And even inorganic molecule like iron pentacarbonyl can be optimized using theoretical calculations. Iron pentacarbonyl can be optimized. And we have optimized even a silicate molecule, and we found the cavity between the four silicon atom as 24 nanometer. So this 24 nanometer, I think we have calculated from XRD and TEM and SEM. But when we do calculation, that also shows the same nanometer dimension. So it can be compared. So this is a useful way of finding uh, support from the theoretical calculations. And this will be useful uh, predicting many things. You can see the one paper, experimental and first principle investigation of the adsorption of entrapping guanine with SiO2 clusters in salt gel silicate material for understanding DNA photocleavage. We have done how it is attached to a uh, zinc oxide nanocluster. Adenine molecule, how it is attached to zinc oxide nanocluster, we have optimized, and we found that there is a hydrogen bonding. There is a bonding between the zinc oxide cluster with the metal, and we further found that it goes to the cavity of silicate. So we report, and it is well received, and uh, the results are available. And not only adenine, we have done for guanine, experimental and first principle of guanine on zinc oxide clusters. And by doing theoretical calculation, what we can do, how different substrates are absorbed on nanometal surface. I think we are all now thinking about nanomaterials, how it is interacting with the different molecules. Here, from starting from a simple molecule, a big molecule are attached to a nanometal surface. When analyte adsorb on the nanometal, this is the key to whether the reaction is catalyzed by how your nanomaterial, whether your nanomaterial is able to sense the material. So whether the nanomaterial is going to be target your disease state, everything can be studied only through the surface interaction. So I'm very much interested to do calculations on how analytes are adsorbed on nanometal surface. So students, you also should know that a simple calculations will lead to a new ideas how it is going to support many new research avenues. So the interaction of different analytes on nanometal will open many research fields And in our case, one of the student, he has done a surface enhanced Raman spectroscopy with rhodium clusters. So we have taken a rhodium nanometal, and we put L16 on that, and how L16 absorbed on the nanometal surface has been studied through theoretical as well as surface enhanced Raman spectroscopy, and we found that it's a wonderful results as produced, and it was published in Physical Chemistry Chemical Physics 2015. So these are the some of the results in that paper. You can see that, and we found that when new peak is producing, new peak, it gives a new frequency. We found that it is surface enhanced infrared absorption. So even though you know that when analyte adsorb on the nanometal surface, there is different phenomena. There is a physisorption or chemisorption. If it is chemisorb, definitely the symmetry changes, right? Symmetry changes, or sometimes there is a formation of new frequencies, new bonds. So we found that, and we concluded that it's a new surface enhanced infrared absorption, which is not visible in ordinary infrared, and they put that in special issue of surface enhanced Raman spectroscopy in PCC. Only two papers have been picked up from India. One is from Hyderabad Central University, one is from Annamalai University. So we are very proud to say that a simple uh, thing, whatever we are doing in the lab or in calculation or a simple day to day, will lead to a big discovery, or sometimes it is going to be useful for predicting whichever we can't predict with our usual tools. And at present, I told you the structures of simple molecules, how molecules are absorbing on the nanometal. I can go for a new class of materials. People are thinking about that, like carbon nanotubes. You can see people are using CNT in different experimental procedures. And CNT, what is carbon nanotube? If somebody asks you whether what are the allotropes of carbon from our 10th class or plus 2 class, we may able to tell carbon has two allotropes. One is diamond, another one is graphite. But now, if I ask a new age student, even their plus one, plus two book, it is there. Carbon is having more allotropes, not only diamond, not only graphite, it is having graphene, carbon nanotubes, and fullerenes, C60. 60 carbons are forming a bulk structure that is called C60. So, carbon is having more allotropes, and here I am showing the allotrope of a carbon. It is called carbon nanotube. If you open, if you cut this CNT, there will be a single two-dimensional layer that is called graphene. So single graphite layer is graphene, and graphene is rolled. It forms carbon nanotube. It may be a multi-wall or it may be a single wall, and it is having wonderful properties. It may be useful in many engineering applications. People think about a lift from Earth to Moon using this carbon nanotube. So you can see how much it is more strength when compared to ordinary pencil. If you write with a pencil, you know that it is made up of graphite. We can rub it with a rubber, right? And but if you take one layer of that pencil mark, that is graphite mark, that is graphene, that is having enormous strength when compared to ordinary graphite. So graphite can be brittle, but graphene will be useful for making high strength applications. So when you go, it's only made up of all our carbon atoms. Okay, six-membered carbon atoms. They can roll it, and when it goes to carbon, hydrogen, nitrogen, interestingly, it forms peptide nanotubes. So how carbon is forming a nanotube-like structure? Even peptides. You know that peptides are made up of two amino acids. two amino acids when joined together, it form a peptide linkage CONH, and many peptide links will give polypeptide, and many polypeptide will give you protein. So proteins are our body building structure in biology or our day-to-day life. We can say that, or we can read that protein is the important body building material. And in this COVID-19, people are advised to take protein supplements. If you take proteins, you are more protective than a normal person. So take protein for uh, against diseases. So we have to address many protein molecules, or what are the properties of that protein molecule. So we can use these peptides can also self-assemble. So what is self-assembly? Self-assembly without external force, it can roll and it makes peptide nanotubes. So this is the comparison between carbon nanotube and peptide nanotube. And peptide nanotubes are very interesting. I told they assemble, self-assemble. So without any force, if you put it in a water, a peptide molecule, they can join together. They can join together by a ring. They form a ring-like structure, and one ring, it can form two ring, three ring, four ring, and it can be stacked one by one. It can be stacked by that, and it can form a tube-like structure. So I compared with our Endiran climax. In Endiran climax, you know that many superstars will join together to form a mega or high energetic villain kind of thing. So, like, of course, this is also doing the same thing, but we can use it for good things. And this is the peptide when assembled. So I can go back to the experimental lab and I check with transmission electron microscope, and whatever we predicted with theory, yes, it can stack and it can form a tube. It can form a big tube like structure. When you go still more resolution, you can see the tube like structure. This is going to be useful for many applications. And we have done some theoretical calculations how silver nanoparticle is attached to the dipeptide or a peptide molecule, so that how nanomaterial can be absorbed to peptide molecule. The results of the optimized structures are given in this figure, and you can see the binding site can be found, and for by different atoms of the peptide, and we found that only the NH2 group is having more binding capacity compared to other things. And using this, we predicted this for sensing, and we can use a nanomaterial for sensing adenine, and it was published in Sensor and Actuator. So students, you can think about by knowing what I want to tell. The analyte, how it absorbs on the nanometal, can be optimized through calculations, and we can think about what is application, real life application. So I can think about sensors. So the same nanometal substrate can be used for sensing different biomolecules. Whatever we have done the calculation, we can go for real life, and we can identify and we can give some product to the society. So now we are all able to think about how to be the virus has to be sensed or bacteria has to be sensed. So these are the work I am thinking about that, and I think in future we may get some results by using nanometal surface how we can protect ourselves. And I told there is a Raman spectroscopy also useful, and different DNA bases, adenine, cytosine, guanine, thymine, are giving different Raman signals when it attached to the nanometal surface. So when analyte attach on the nanometal surface, it will be useful for sensing as well as surface enhanced Raman scattering studies. So people will do uh, research people in my group, they will do sensing, surface enhanced Raman, catalysis, all properties whichever we learned or we have tried to get from theoretical calculations. And these are the some results. Theoretical also is included. So this is the theoretical Raman spectra simulated when analyte aziendol adsorb on the nanometal surface. These are the experimental Raman spectrum. So you can see that how it is comparable, how it is comparable to the experimental one. And this we published as a book chapter, and you can get this book chapter in the uh, stores, online stores. It is available. And uh, I have told you a theoretical explanation of polywater. I have told in my talk very initially, we have to use all theoretical calculations judicially. Why we have to use judicially? Why I told we can't optimize all the structure whatever we think in our mind, whether it is really possible or not, that we have to first think. So you can see people in 1970, they have published a paper, and they told there is the possibility of existence of polywater. So they told two or three water molecule can combine and it can form a polywater. And polywater has very interesting properties, peculiar properties when compared to ordinary water. They told like that, and people started theoretical calculation on that, and they also supported the findings of polywater. So there is so many publications on this polywater has produced. People started pouring research on polywater, but one day it was found is totally impossible. There is no polywater. So it is only a fictitious or fake result. So there is no experimental evidence of polywater. So uh, now people started thinking about what is the use of theoretical calculation. So theoretical calculation will be helpful for supporting even fake results. That's what I want to tell to the fellow researchers, students. You have to go, or you have to have some ethics. You should know some fundamentals of judicially applied theoretical calculations. After getting experimental results, to support the experimental result, we can use theoretical calculations. Instead of doing whatever structure you want to do optimization or doing something for a research purpose, it may not be advised. So for MSc students, I want to tell in this talk what I told, or what are the things I have explained. So from starting from the structure of a molecule, you take a structure of a molecule. We have to know the structure of the molecule. For that, group theory is going to be useful. For that, quantum mechanics or quantum chemistry is going to be useful. For that, spectroscopy is going to be useful. And for that, finally, computational techniques are also going to be useful. So you should know all the fundamentals before going to the theoretical calculation. If you think about water, whatever we studied water, you think about that. In what aspects we have studied water, just you think. I'll give 1 second or 2 second time. Students, just you think. Where are the places we studied water? Okay. Now you can think about where are the places we have studied water. Water we studied with the structure of water. What is the C2 axis? Water is having C2 axis. C2 means 180-degree rotation. If you do 180-degree rotation, it will give again the same structure. So it is having C2V point group, and it is having dipole moment. Why it is having dipole moment? There is a polarity is there, and it is having hydrogen bonding. That's why it exists in liquid form. And we have studied phase rule of water, single component system, and we have studied higher frequency of water, 3n minus 5 vibrations are possible. So 3 into 3, 9 minus 5, it is a non-linear molecule. So 3n minus 6. So it is having three vibration: symmetric stretching, anti-symmetric stretching, and there is a bending vibration. So if it is symmetric, the molecule is symmetric, we apply 3n minus 5 formula. If it is non-symmetric, we apply 3n minus 6 formula. So we have studied water molecule in group theory, and we predict IR and Raman spectra of water molecules. Like that, in many places we studied water. Right? Water is a universal solvent. We have been taught by our 10th class teachers. Why it is universal solvent? It is having polar nature, and so by thinking simple molecule in our mind, we can compare or we can get some knowledge about chemistry. So chemistry is interconnected. Whatever we studied in different places, it will all connected through one point. If you find that point, you understand chemistry, and you can do whatever theoretical or whatever experimental or whatever competitive examination you want to pass. First, try to understand the basic concept. I explain, and uh, I have to tell some of the points uh, in electron microscope. I told this is a transmission electron microscope. I said that. So, and you can see the electron microscope. It tells how the electrons are looked like in your material that can be seen through microscope. And this is where I have worked, and this is he's my guide, and various places I worked, and I got some ideas. I hope whatever ideas, whatever I told, it should be reached in your mind. And if you have any questions, you can just mail me, and I'm very willing to help you all. I once again thank the organizers for giving me an opportunity to share some of my thoughts on quantum chemical calculations. I hope really you are all enjoyed the session. Thank you very much. Thank you, sir. Thank you.
Thank you, sir. I hope participant will attend the entire session. This, I hope this useful information to you, sir. Thank you so much, and thank you for accepting your invitation. Now I call upon Professor B. Sangeeta to deliver a vote of thanks.
Good morning to everyone. I am very glad to take this opportunity to deliver vote of thanks for a 2-week online lecture on free online competitive exam coaching for chemistry organized by Department of Chemistry with Internal Quality Assurance Cell, Dr. R.K. Shanmugam College of Arts and Science, Kallakurichi. First of all, I thank the management for accepting this online program. Thank you, sir. And I would like thank to our principal IQAC chairman for the principal address. Thank you, sir. And also I thank our vice principal, Dr. P. John Victor, for the felicitation address. Thank you, sir. And also I thank our HOD, Dr. J. Ahmad Sultan, for welcome address. Thank you, sir. I am very glad to thank for the resource person of the day, Professor of Physical Chemistry, Dr. KARTHIKEYAN, Annamalai University, Chidambaram, for the excellent presentation for computational chemistry for spectroscopy, group theory, extra examples for this topic. Thank you, sir. And thank everyone for the organizing committee, participants. Thank you, one and all. Thank you, sir.
Thank you, sir. Thank you.
Thank you, madam. Thank you, sir. Thank you, madam. On behalf of the Department of Chemistry and Internal Quality Assurance, sir, I personally thank sir.
Thank you, sir. Thank you very much.
Thank you so much. Thank you for accepting the invitation. Thank you.